Circular motion, more and more and more. Today, we're going to handle a little bit of a different story. Today, we're going to be dealing with cars that are on a curved bank. Last time we did like a roller coaster and the little loop-de-loo like this, and we did the forces of it as it went around. But this time we're going to make our life a little bit more different. So like think like a racetrack, and on these like NASCAR racetracks that kind of look like a oval, an elongated oval like this. At these areas on the side, if you ever actually watch the races, you see that the curves around the side are banked. Yeah, they're banked or slanted. So whenever we look at the curve, it actually looks like you're on a triangle like this, and the car is actually like I'm gonna I'm gonna try to make this. It's well, I mean, does that actually help? It kind of makes sense that like if the banking is up and not down, that you can actually take the corner faster. So we're gonna see ideally, ultimately, like how that actually works. And the deal is that we're gonna use centripetal force in that calculation. Because if you were, let's just pretend that it wasn't banked and it was just flat. So I'm gonna do like banked versus flat ground, and this is gonna be a car, and the car is like, yeah, it's a square car. So beep beep. If the square car is going like straight across this way, what are the forces that are acting on it if it is actually turning? Let's just pretend that this car is like right here. Okay. Inertia. Hang on now though. But inertia is not a force. It does. You're right. It does have inertia, but inertia is not a force in and of itself. So, of what? Okay. Okay. So I'm going to put those applied forces over here. So let's say that it's moving this way. There's an applied force going this direction, right? And friction is going this way. Force of friction. Okay. There's a couple of other forces acting here as well too. Yeah, so like since I'm looking at that from a top view, I'm now going to go over to the side view and I'm going to say, okay, well, there is gravity going down this way, mg, right? Is the car Hulk smashing through the road? No. The car is definitely not Hulk smashing through the road, so there's a normal force going on too. Okay, now if this was the case of all the forces that we have, then this thing would do this. Whee! And it would continue going along the line of action, and it wouldn't curve. So there has to be another force. There has to be a centripetal force that's holding it in. So when the wheels turn, what do they do? Let's see, it's going this way. So why don't we say that this way is the centripetal force? So I'm going to call that Fc for centripetal force. Now remember that centripetal force is actually something, right? Okay. So we could do that. Yeah. So like the centripetal force, if we're going to measure it out, is equal to mv squared over r. So as long as you've got a speed and you've got a radius, you're okay. So if it was just on a flat ground, then that would be what you have, right? Okay. So since it's slanted and it's banked, you know what? I'm actually going to draw my banking the other way to keep us from having like a mirror image crisis, because I was getting ready to have a mirror image crisis. Since it's turning this direction on the track, I'm going to just draw it this way, and I'm going to put the car up here like this. There, there we go. Okay, so it's turning, it's going around this direction, and if we draw some forces on this one as well too, what forces do we have acting on it? There is a normal force like this, right? Oh, what's wrong with that? Has to be perpendicular. Okay, has to be perpendicular. Okay, so I'm going to write N for normal force. Okay, F of G goes, are we all in agreement? Thank you. Please don't miss that on the AP Physics test. Force of gravity goes down. Okay, don't worry, that happens automatically anyway. You don't have to do something just to make me look bad. That already happens. So I don't have to really worry too much about that. Okay? So let's not. Please don't. Please don't. There's too much at stake. College credit is at stake for you guys. No, 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 no. All right, so we know that there's actually two forces that are centripetal here. Okay, so we actually have to add both of those forces together. So in the case of the banked car, there is a slope. There's a car going around on a slope, and there's also the force of the friction as well. Okay, so friction will pull this thing back, but friction will also cause this thing to go around in the curve itself because y'all said it's the tires that are turning that are actually causing it to actually turn. So therefore, it's the friction between the tires and the road that's going to actually get this thing to move. So the centripetal force is friction. Okay. Also, there is an unbalanced force on this object. So I know it's really tempting to want to draw an arrow that goes this direction, but it's not there, okay? Because there is an unbalanced force acting on this object, which means it's accelerating, which is why it's turning, okay? So even if it's going at a constant speed, the constant changing direction is an acceleration. So it is tempting to draw that arrow on the right side, on the far one, but you don't want to. You don't want to put an arrow right here because there is no other force acting in that direction. Okay? All right. So now if we're going to try to solve this to actually try to find out what the centripetal force acting on this is, um, or what we can actually do is we can say, we can add some numbers to this, which I think is probably a good idea. Let's say that the embankment right here has an angle of 9.2 degrees. Okay? And let's say that the radius for each corner is 256 meters. So I'm going to just make a radius that goes out. So I'm going to say that this radius is 256 meters. Okay. Um, Now we want to say how fast, what is the fastest possible speed that a car could actually take on this corner if we have a coefficient of static friction of 0.550. So we were talking about how friction was the driving force behind these. We're going to need a number for the friction. So if friction is 0.550, then how fast could we actually take this turn before we end up sliding one direction? And in this case, if you're going too fast, you're going to want to make a bigger circle, so you're going to end up sliding off of the track, not closer in. So if you slide off of the track and it's a race, you're sliding into the wall. Yeah, exactly. It's not going to be happy. It's not a fun time. So we're looking for the maximum speed. Okay, max speed. Okay, so what I got to think about this. We're going in a circle, right? So the kinematic equations are out the window. So VF squared equals VI squared plus 2AD, can't use that. VF equals VI plus AT, can't use that. Why? Because we're going in a circle. Okay, I know it is, but we have to deal with it. Okay, so let's think about this and let's add together. So like, let's go back to this. It's a regular force problem. So the question I'm going to ask you guys is it moving? Okay. So is it moving? Yes. Okay. Accelerating? Yeah, it is. So yes, but it's in a circle, right? So I'm just going to write a circle down here. So that means that we've got v squared over r. So um, if we make our line of action on a curved embankment like this, our line of action is kind of going to go like this. Our line of action is up the ramp, and along the normal force. That's our coordinate system. Okay. So the circle part is going to be the part that's actually wanting to go this direction into the circle. Okay. And we're going to try to find out how fast we can actually go. Because I know that if we're going in a circle, there's a v squared over r. So let's sum up our forces. Let's split this up. Let's do x direction and let's do y direction. Okay, there's a reason why I had to teach you guys x and y directions before we got to circles. And, well, this is one of those reasons. Okay, so in the x direction, what forces do we have acting here? Okay, so friction, and that would be the one going which one? So, all right, let's just add them together. Sum of the forces in the x direction is going to equal friction, okay, and is there anything else that's going to be pulling it into the circle? I'm going to move this y over a little bit. What is it? FC. FC is going to be both of these put together because we have a centripetal force wanting to go in, okay? So the direction, like towards the center of the circle, is actually like, oops, towards the center of the circle is actually this direction. I cannot draw a horizontal line to save my life. I'm going to try again. There we go. Towards the center of the circle is this way, okay? This makes our life a little bit complicated. Okay. The circle is FF. What do you mean? Oh no, yeah. These are separate from each other. Yeah, don't automatically try to connect these two together. So y'all are missing something. It's not just the friction. What's causing it to accelerate? No, not the applied force. The fact that it has to turn. Okay, that's the friction part. There is one more force that's acting here that's going to make it go into the circle. Yes, the bank. What about the bank? It's an angle. It's a component, yes. It is gonna be the it's gonna be the sine. Hang on. Y'all are saying a lot of fancy things, but I'm looking for the basic. Like friction and what's causing it to go down the hill. Gravity is causing it to go down the hill. So we've got we've got friction, we've got friction, and we've got gravity that we have to worry about, right? We've got friction and we have gravity that we have to worry about. Now, in this case, this gravity is an x component, right? So I'm going to put x here. And this friction is also an x component, right? Okay. Okay, now wait. Because gravity is actually okay. Let's go back. Let's go back and let me just focus in on this part right here. Okay. Hang on. Let me explain. Let me explain before we get confused. Why is gravity have an x component? Is because if you're going down the slope and gravity is pointing straight down like this, then you actually have to break it down into its normal force component and its x component. So this is the x and this is the y, quote unquote. Okay? So it's like cosine of it's not going to be the cosine because the angle that we're using is going to be based off of that 9.2 degrees. And that 9.2 degree similar triangle is not the not the cosine, but the sine. Okay? Right. I'm going to get rid of this now. So we have our x and we have our y. So down this direction, this is going to be mg sine theta. Okay? Are we all okay with that? Now, the force of friction, you are more than welcome to use the cosine of that angle because the cosine is going to be the horizontal one. Okay? So, here's an interesting part. Now, for friction, we have to ask ourselves one of two things. Okay? Um, is this static or kinetic? Why? That's not always true. What about wheels? What about wheels makes that special? Okay. Now wait a minute. Hang on, hang on. I need y'all to think about this really carefully. Okay. Whenever wheels turn, this actually counts as static friction because, because, because the wheel actually never slides on the ground. Okay. Because as the wheel turns, the bottom part comes into contact with the surface below, but then as it continues to roll, it just keeps mashing against the surface. It doesn't actually slide. For a kinetic friction to occur, there has to be some sliding that occurs in order for this to happen. Okay? So, if we know that this is going to be static friction, we can say that that's going to be, well, friction is fun, right? So that's mu sub s for static in, but it's not the entire length of this. It's only the x direction. So it's going to be mu sub s in cosine theta. Okay? Because remember I said this way was towards the center of the circle, right? This way is good. Well, look at the direction that n is pointing. N is pointing in this direction. So if we were to try to break the n up into its components, then the n is going to be cosine this way and sine this way. Okay, that probably hurts a little bit, but that is what it is. Okay, it is what it is. We don't have much of an option on that one. Okay, and since it is a moving force, since there is acceleration happening, all of this is equal to what? Mass times acceleration. What kind of acceleration? So I can change this acceleration to a, which means I can change the AC to a, it is not an air conditioning unit, no. There we go, mv squared over r. mv squared over r. It is, but ultimately remember, whenever we're looking for this, we're looking for the maximum speed, which means instead of having mass times acceleration, it's probably going to be better for us to have mv squared over r instead of mass times acceleration. They are the same thing. I'm not going to argue that they're not the same thing because I would be very wrong. They are the same thing. Okay? That is our x direction, right? I think that we can we get everything for can we get everything in here? Let's see. Hmm. Hmm. Okay. What happened? Yeah. Okay. So let's say, I mean, like, we've got the normal force, right? We've got the static friction. We've got that it's equal to mv squared over r. So I think in terms of, we've got the radius, um, but we don't have the mass of the car. Uh-oh. Well, you're right. I never really did put the mass. They they didn't give it to us in the problem. You can't Google this one. They didn't give it to us in the problem. Mass isn't actually given to. You're right. We don't need it, but prove that to me. Like, what do you mean we don't need it? So we're trying to find the max speed. Yep. But we're all the way down here. We've already broken our forces down. The normal force is related to something. Is it exactly the weight of gravity this time, though? Okay, it's not exactly the weight of gravity. Okay, so we've already taken that into account, right? That we've said that this is the cosine theta. Okay, so let's not make this any harder than it is. Okay, the mu sub s, the n is equivalent to mg, right? Because the cosine theta is that horizontal component that goes across here, plus mg sine theta equals mv squared over r. Well, wait a minute. No, it's not that mv squared over r is equal to n. It's just that we just took n and we said, oh, hey, the normal force going up was equal to the force of gravity cosine theta going down, right? we're having a moment. We're having a moment. Hmm. Think we're okay? All right. At this point, everybody brought mass to the party. So if, so if everybody brought mass to the party, then the mass ends up canceling out. Boom, boom, boom. Okay. That's all gone. We don't need the mass. It cancels. Okay. So now that the mass canceled, we can solve for velocity. Okay. We can solve for velocity. So v squared over r. Let's go ahead and just get rid of the m's. Okay, it's mu sub s g cosine theta plus g sine theta. Okay. Looks like we need to multiply everything by r, right? Okay, so v squared. Hey, these have a g in common with each other. So they don't cancel, but I could do something if I was clever with algebra. I could pull it out. I'm going to undistribute it. Okay? Yeah, pulling it out is undistributing, also known as unfoiling. If it was a quadratic, it would be unfoiling, right? Yeah. It's okay. We'll just say we're undistributing it, and that's fine. So it's G R, and then we'll go ahead and put everything else in parentheses. Mu sub s cosine theta plus sine theta. Make sure I didn't leave any letters of my alphabet soup out. And then if I want to get the final answer for the velocity, I'm just going to square root that. I just like destroyed it. Like take your entire expression and just like, there we go. Okay, so if we were looking for the top speed of that, this would be our expression that we were using. I think we can actually plug something in and not let it explode. If we typed in the coefficient of friction and the angle and gravity on Earth, we would have that. I think probably the most important thing to note with this one is that the mass actually ended up canceling out and it did not matter. Okay, which means that there is a maximum speed for any vehicle to go across that road at that embankment, which means that whenever they give you like the traffic people, whenever they have a speed limit around specific corners, those were tested, and it doesn't really matter what the mass of the object is. It still has the same acceleration value. That's the best speed you can take it without it actually moving over. So like if they give you if they give you a value and they're like, "Oh, you can't take this past 90 miles per hour," they'll bump it down to like 55, because they'll give you a well safe limit because if you tell somebody to do something and you design it to be that sharp, chances are people and you'd be like, "Oh, don't take this past 55." Chances are some people will actually do it anyway. So if it's designed for 90, you set it down to 55 and that's it. Yeah. Okay. We. All right. Let's let's talk about two different things that I've kind of not wanted to talk about yet, but I think we're probably ready now. Um, and that's the difference between centripetal and centrifugal. Well, no, that's not really how that works. Correct. One of them is fictitious. So we consider the centrifugal force a fictitious force. Fictitious. I don't know how to spell fictitious. IOUS. Fictitious. Okay, there you go. Okay. And the centripetal force is actually like a legit force. Now, the reason why we actually call the centrifugal force a fictitious force is because most of the time you don't actually that force doesn't really exist. So, in the case of let's take for example, if you're going around in a car and you're inside the car, okay, and you're going this way. Now, you have a centripetal acceleration that goes this way, but you feel yourself pushing against the door of the car. So like if somebody is like just swerves really quickly, yes, that's going to try to keep you into a circle. There is a center seeking force, but you feel the actual force of the object going the other direction. So what this is over here, this is inertia. So this force, this quote unquote fictitious force, this is just your inertia. This is your object in motion wanting to stay in motion. So therefore, this isn't actually really a force. Therefore, there is an unbalanced force acting on you. This centripetal force keeps you in the circle, and there is an unbalanced force acting here. Okay. Do what? Okay. Yeah, that's true. What is that? The cyclotron or whatever they call it? So that fair ride is an object and it kind of looks like a big saucer like this. And you put humans on the side and you start spinning it really, really fast, right? So as you start spinning around and around and around, it's the same concept. Your inertia is what's keeping you pinned against the back of the wall. There is actually a center seeking force that's acting on you that is trying to keep you in the circle. But your inertia is this fake force that you feel going this direction that seems to be quote unquote pinning you back to the thing. Okay, so this part back here, this is fictitious. Okay, the one that actually goes inside is the force that actually keeps you in the circle. Okay, so you only feel, you only feel the, okay, let's see. If you're in some kind of frame of reference that has your inertia as the inertia of everything else around you, then the centrifugal force doesn't really show up. Okay, so like I need you to kind of think about this. If you're in a reference frame where your inertia actually is spinning or it's moving around in a circle, you're gonna quote unquote feel some kind of fictitious force acting on you. Okay, does that kind of make sense? So, um, if you are on a merry-go-round, if you are spinning here, you're gonna feel that force. But if you're out here looking at the dude that's spinning around, you're not going to observe a force at all. Okay? So the only thing that this person's going to say is this person is going to say there's one force and that one force keeps him in the circle. The other person is going to say, "Oh, well there's two forces. One force is keeping me in the circle, and the other one that I feel is smushing me back against the back bars." If y'all have ever been on a merry-go-round before, I know they started taking those out because people like literally legit hurt themselves with it. But if you've ever been on one before, you can actually feel yourself being pulled back, or like whenever you're in a car. It's very easy when you're actually part of the spinning system to say that there are two forces acting on it, But if you are not part of the spinning system, it is very easily to logically get rid of that second force. Okay? And that's the difference between centripetal force and centrifugal force. Okay? Things get a little bit more complicated if you start thinking about like actually being on the spinning system, because whenever you're dealing with a centrifugal force on a spinning system, there actually is like you can actually register a second force. So like the earth is spinning around on us right now, so we're all spinning at the same speed roughly. That's why we're not like flying past each other. If the world were to suddenly stop, we would all move in like our inertia would keep us all moving. Everything on the surface of the earth would just get like snapped off as the earth just stopped. That would take a tremendous amount of energy to be able to do. It would be catastrophic. It would be the true definition of catastrophic. Okay, say goodbye to everything, is what would happen there. So, but we actually have to account for a centrifugal force. So if you're doing things that are moving very fast, like airplanes, jets, and such, they actually do have to take into account centrifugal force because the entire Earth is spinning. What we normally do is we ignore the fact that we're on a giant rotating system and we say, you know what, we're pretty much just stationary. So if you're on a stationary thing, you only have to worry about centripetal force. If you're on a rotating system, you have to worry about centrifugal force. Okay? For AP Physics, you can, by and large, just get rid of this completely. Okay? You don't really have to even worry about it too bad. Okay? The centripetal force is going to be the only one that you're going to see like super often. Okay? Um, you can ignore the other one. All right? Y'all have any questions? Everybody okay so far? Y'all still alive? Still alive? That's disturbing. Do y'all want to try another force problem dealing with the dynamics of this, or do you want to move on? That does. That actually does make a lot of sense. So like we're almost there. Almost there. Okay. Okay. Let's you know what? Let's try one more. That deals with these angles because I think these angles are going to be what's kind of disturbing you guys the most. Let's see if I can find another one that's not as like super crazy. This one going this direction. Um, okay. Let's try this. Let's do an airplane one. Hey, airplanes are our friend. Okay, so we're gonna say that we have an airplane, and this airplane looks like this. Yay, airplane. Okay, it's an airplane. It's a very happy airplane. We're good. And this airplane, we have a couple of different things for it. Oh, no, we actually might not. It says that it's going to banks, it dips its wing to one side to turn in that direction. By banking the plane, the lift force, a force exerted perpendicular to the direction of flight due to the motion of air over the airplane's wings, ends up with both a vertical and a horizontal component. Okay? So we're going to try to look at these force diagrams and we're going to see what we can actually get going. So like if you're not turning, because this thing is actually trying to go like in a circle, okay? But if you're not going in a circle of itself, then there's a couple of forces acting on it. So like I'm just going to write up here, not turning. Okay? If we're not turning, what forces do we have acting on an airplane? What are all of them? Okay. Gravity going down, right? Yeah, we're going to count air resistance as friction. So we've got F of G, gravity going down. Okay. What do we have going up? Is there anything going up? Okay. So the wind resistance is holding it up. We're going to call that lift. Okay. That comes from the actual wings on the plane. The wings on the plane, whenever air passes through it, from the way that they're designed, provides a lift, an upward force on the object itself. So we don't really necessarily call that air resistance. We call that lift. There is an applied force that goes forward that keeps the airplane going forward. And there's also a force that goes backwards, but I don't want to call that air resistance either. We're going to call that drag. Okay, so if you're dealing with, and the main difference between friction and like air resistance is if you're actually dealing with a vehicle that's moving, you don't really want to call that air resistance because that only deals with like things that you throw. If it's a vehicle, you want to call it drag. It's moving through a fluid. So anytime there's air resisting you in a fluid and this object is moving, that's going to be called drag. Okay, right? Air is a fluid. Yeah, yeah, that's true. Yeah. Yeah, a liquid is a fluid and a gas is a fluid. So they actually behave very similar to each other in several circumstances. Gases are a lot less dense, but if you're talking about like how things diffuse, liquids and gases have a lot more in common with each other than they do solids. So we call both of those fluids. I know a lot of y'all are thinking that fluids are normally liquids only, but it's actually considered both. Okay, now let's actually like turn this a little bit. So instead of it actually moving this way, it's going to turn a little bit so that there's a lift angle that goes this direction. Okay, so it's like it's not straight up and down. There's an angle that goes along with it. Okay, it's going to be a slight lift angle. Okay, does that make sense? So is there a centripetal force? Okay, what about when it is turning though? So like if it's not turning, then the wings are just straight up and down like this. Like the wing would be here and the wing would be here. Okay? When it is turning, the wings are going to tilt this way. What happens to the lift? Okay? The lift force is always going to be perpendicular. It works like a normal force. Okay? So we're not going to add both of them. We're not going to consider both of them individually. We're just going to say that both of these together is a lift force because you just end up adding them anyway. Okay? So there's an angle that goes right here. Okay? This is the lift. So we can either write lift or we can write FL. Either one of those is fine by me. Um, it's okay either way. Okay? So, um, how are we going to figure out? Well, I guess there's a couple of different things that we can figure out. Um, if it's moving at a certain speed, how far is the radius going to be that it actually turns? So whenever it turns through the circle, there's a certain radius value that it can turn, and your angle determines how fast you can turn. Your radius, the steeper you make it, the quicker that radius or the shorter that radius can be. So what I want to know is what is this radius value? How fast can we get it to go? We're assuming that this plane is moving forward at some velocity v. Okay, so can we figure this out? It would still have drag. Yeah, it would still have drag. And it would still have an applied force too. It would still have both. The applied force and the drag, since it's going at a constant speed, are going to be equal to each other. Yes, that is true. Okay. So that means that, like, in this direction, both of these are going to be pretty uninteresting because the applied force and the drag just end up canceling each other out. Gravity is going to be definitely an interesting factor. The gravity and the lift are going to be interesting compared to each other. So the first question I'm going to ask you is it moving? Okay, right. If not, you have a problem. Yes. Is it accelerating? Okay. It's a circle, right? So it's a circle? So what's that mean? Well, that'd be a semicircle then. If it just goes in half the circle, that still counts as a circle. So like if you did this, if you were like do 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 meow do 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 do. Okay, this part right here, this would be linear. Okay, your linear forces would apply. So in this case, your forces would be balanced, and the sum of your oh god, that's supposed to be a sigma. It's supposed to be balanced, and the sum of your forces during this part is going to equal 0. Over here, the sum of your forces, because this is circular, is going to equal mv squared over r. Okay, it's still constant. You're still going to end up being balanced. If you treated this semicircle like it was a linear one, you're going to get the sum of the forces equal to 0 because you didn't account for the fact that it was going in a circle. Okay, so like, is there an acceleration happening on this part right here? So like, there would be no acceleration here. There would be acceleration in the semicircle, and when you're back on the linear part, it would be no again. Okay, so it depends. If this airplane is just moving in a straight line, I would answer these first two questions very differently than is if it was moving in a circle. Okay, so since I know that it's going in a circle, I know that I can add up the forces. So I can either do the x or the y direction. One of them is going to be interesting to me. The other one is not going to be interesting to me. Y will be interesting. Y will not be interesting. Okay, I'm gonna get rid of this radius. Bloop. Goodbye, radius. Uh, okay. Then let's do with x. We are turning. We are turning. Yeah, we are turning. Okay. So let's go. Like, I think we're going to be looking at it from this direction, right? Ah, crap. Time to go. We'll continue this tomorrow. Have fun. Enjoy your day.